Hello everyone. Today we're going to look at the rational root theorem, which is just a theorem that we use in order to determine all of the rational roots of a polynomial function. Now before we have to distinguish the difference between a rational root and an irrational root, which are, remember that roots are also called the zeros. So this is an example of a polynomial that would give me rational zeros. So if I make this equal to 0 and solve, I can factor this to be x minus 6, x minus 1, which then leaves me with the zeros, x is equal to 6 and 1 if I set each factor equal to 0. However, this would give me irrational numbers, and I'll show you how that works. So if we have this polynomial x squared minus 5 and I make it equal to 0, in order to solve for x, I would have to add the 5, so x squared would equal to 5. And then we would square root, which would give me the zeros x is equal to plus or minus the square root of 5. Since the square root of 5 is not a number, like a rational number, and what that means is a rational number is anything that could, like any whole number or any fraction. However, if you put the square root of 5 into the calculator, you're going to get a decimal that goes on forever and ever without any repeating pattern, meaning it is an irrational number. So now the rational root theorem, it helps us figure out what the rational zeros are, not the irrational, hence the name rational root. Now we use this theorem only when we cannot factor the polynomial that's given to us, like in this example is able to factor and find those roots. There is no need to use the rational root theorem. However, if I have a really long polynomial, I don't know how to factor, that's when we would use this. And what this does is basically we take the coefficients, we take the factors of the constant term and we divide it by the factors of the leading coefficient. And then what that's going to do is give us a list of all of the possible rational roots. So instead of starting with an infinite amount of numbers of roots that we have no idea which one it could possibly be, at least this will give us a list for which we would test. So let's see how this works. Here we have this polynomial x cubed plus 2x squared minus 5x minus 6. If I wanted to try factoring this, I wouldn't necessarily be able to, simply because we have 4 terms here, so we could try factoring by grouping, but this second group would not be able to be factored. So we have to find another way. So in order to figure out these roots, first we're going to take the factors of the constant. This is the constant. This is p. So what we look at, what numbers could multiply to give me 6? And that would be plus or minus 1, 2, 3, or 6. Simply because 1 times 6 would give us 6, and 2 times 3 would also give us 6. However, this is a negative 6. So the reason why I put plus or minus is because it could be positive 1 and negative 6, or negative 1 and positive 6, etc. So when we're testing these numbers, we have to test both the positive and the negative versions. For factors of the coefficient that we're talking about is of the leading term. So this is q. So factors of 1 is just plus or minus 1. That's basically it. So the possible factors of the polynomial is when we divide p over q. And that would give us a list. So all of these numbers divided by 1 would just give me the list of plus or minus 1, 2, 3, and 6. So now what do I do with these numbers here? So these are all of my possible factors. As you can see, we have all the positive versions, so 1, 2, 3, and 6, as well as all the negative versions, negative 1, negative 2, negative 3, and negative 6. We're going to have to test which one of these is a 0. Okay, so it doesn't necessarily mean you're going to test all 8 possible roots. You're just going to test until you find one that works. Okay, so and the way we test it is by using synthetic division. You could also use long division, but that would be a little bit more work. So we're just going to use synthetic. So I always go in the same pattern. I'm going to start with positive 1 and see if that works. I write out my coefficients of the polynomial, so 1, 2, negative 5, and negative 6. Bring down the 1. 1 times 1 is 1. This is 3. 3 times 1 is 3. Negative 5 times 3 is negative 2. Negative 2 times 1 is negative 2. And I get here a remainder of negative 8. So remember, because of the factor theorem, if you end up with a remainder, then that means that this is not a factor. So therefore, 1 is not going to be a root of my polynomial. So let's now move on to negative 1 and see if that works. 1, 2, negative 5, negative 6. Bring down the 1. 1 times negative 1 is negative 1. 2 minus 1 is 1. 1 times negative 1 is negative 1. This is negative 6. Negative 6 times negative 1 is 6. And we end up with 0. So I'm going to start off my list here already. X is equal to negative 1 is an answer. Now, in order to get the rest of it, since this was a cubic function, that means that this is a quadratic function, which I know how to factor quadratics. So we can write this out as x squared plus x minus 6. We're going to make it equal to 0 to then find the rest of those roots. And the two numbers that would multiply to give me negative 6 and add to give me a positive 1 would be 3 and negative 2. So my factors would be x plus 3, x minus 2. Giving me the rest of my roots, which is x is negative 3 and positive 2. So these are all of my roots here. Now keep in mind, if you want to know, did I get all of the roots? The highest exponent tells us how many roots we're going to have. So if my highest exponent is 3, remember I'm going to have 3 roots, which I have all 3 here, so we're good to go. Let's try another example. So first I need to make a list of all of my possible roots, keeping in mind that this is P and this is Q. So we're going to write out what is P divided by Q. So all of the factors of 6, which would be plus or minus 1, 2, 3, and 6. And then all of the factors of 2, which is plus or minus 1 and 2. Now when you have multiple factors of Q, then when you're writing out your list, you take all of the factors of P and divide it by the first factor of Q. So 1, 2, 3, 6 divided by 1 is just 1, 2, 3, and 6. And then you also have to divide it by the second factor of Q, which is 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1, which is already on my list. 3 divided by 2 is 3/2. And 6 divided by 2 is 3, which is already on my list. So these are all of my possible factors for this particular polynomial. So let's go ahead and see if we can start testing and see which one would work. So I'm going to start with 1. I'm going to write my polynomial here, the coefficients. So 2, 1, negative 7, and negative 6. Bring down the 2. 2 times 1 is 2. 1 plus 2 is 3. 3 times 1 is 3. Negative 7 plus 3 is negative 4. Negative 4 times 1 is negative 4. And we end up with a remainder of negative 10. So this does not work. Let's now test out negative 1. 2, 1, negative 7, negative 6. Bring down the 2. 2 times negative 1 is negative 2. 1 minus 2 is negative 1. Negative 1 times 1 is 1. Here we get negative 6. Negative 6 times negative 1 is 6. And we end up with a remainder of 0. So I'm going to start my list up here. So x is equal to negative 1 is one of my roots. Now again, this is a cubic function. So that means that this answer here is a quadratic. So I can write this as 2x squared minus x minus 6, and we're going to make it equal to 0. Now to figure out the rest of your roots, you can do one of two things. You can either use the quadratic formula, because the quadratic formula gives you the roots, or you can factor using the AC method, which is usually my method of choice. So I'm going to factor using the AC method. So AC in this case is 2 times negative 6, so negative 12. And remember that then we have to find what two numbers multiply to give me negative 12, but add to give me B, which is negative 1. And those two numbers would be negative 4 and 3. So now I will rewrite this quadratic using those two numbers. So 2x squared, and remember that this represents B. So I am replacing negative x with these two numbers. So negative 4x plus 3x minus 6. And now we factor by grouping. The 2x squared minus 4x, they both have a 2x in common. And when I factor out the 2x, I'm left with x minus 2. 3x minus 6 has a 3 in common, so I can factor out a positive 3, leaving me with x minus 2. Remember that at this point, you'll know if you've done this right if what you have inside the parentheses is the same. And what's inside of the parentheses, that's what we factor out, and that's one of our factors, x minus 2, and then what's left over is the second factor, so 2x plus 3. And now we solve. So we have x minus 2 is equal to 0, and 2x plus 3 is equal to 0. Add the 2, we get that x is equal to 2. Then subtract the 3, we get 2x is equal to negative 3, and divide the 2. And so we end up with our remaining factors of 2 and negative 3 over 2. So remember, a couple things that you can do to check your answer. We have 3 zeros, which is what the equation said we should have. And also, all of these numbers here are on our list. Remember that these all are positive or negative. We have the negative 1, we have the 2, and then the negative 3 over 2. Let's try another one. Now here, this one says solve the polynomial equation below. It's just another way of saying the same thing. Find the roots, because as you can see from this polynomial, it equals to 0. So we're going to find all of those roots. Now here we have P as 18 and Q as 1. If I were to try factoring, this is 5 terms. It's very difficult, which is why we're using the rational root theorem. So let's start off with P over Q. The factors of 18, let's see, 1, 2, 3, 6, 9, and 18. Keeping in mind that it's 1 times 18, 2 times 9, 3 times 6, all give us 18. And remember, it's always plus or minus because of it could be positive 1, positive 18, or negative 1, negative 18. And we're going to divide this all by factors of Q, which is just 1. So everything divided by 1 is just the exact same thing. So the factors that we have to test are 1, 2, 3, 6, 9, and 18. Now something that I would like to bring up. You see how this is to the 4th. That means that once I test a number, I'm going to end up with a cubic polynomial. And you could see if you could probably factor that cubic polynomial, but most of the time you probably can't. So then you would have to test yet another number and make sure that that would work as well. So let's try this out. Okay, let's first start off with 1, because why not? I always start with 1. Let's write out these numbers. So 1, 1, negative 11, negative 9, and 18. Bring down the 1. 1 times 1 is 1. This is 2. 2 times 1 is 2. Negative 11 plus 2 is negative 9. Negative 9 times 1 is negative 9. Negative 9 minus 9 is negative 18. And negative 18 times 1 is negative 18, leaving me with a remainder of 0. So right away, I know that x is equal to 1. That is one of my roots since I end up with 1. Now this is a cubic function. Let's see if we could possibly factor by grouping. So this is x cubed plus 2x squared minus 9x minus 18, and we're going to make that equal to 0. So these two have an x squared in common, leaving me with x plus 2. And then these two have a negative 9 in common, also leaving me with x plus 2. So this actually works. We can actually factor by grouping. Let's say in the event that you were to do this and you were not able to factor by grouping, then you would have to pick another number from your list here to test it, but you would test it using these new numbers down here, rather than numbers of the new polynomial. So let's continue with this problem. So x plus 2 is one of my factors, and then x squared minus 9 is my other factor, which we can actually continue factoring, right? Because that's a difference of squares. So we have the x plus 2, and then this difference of squares is x plus 3, x minus 3. Since remember, when you're factoring a difference of squares, you square root the first term, square root the second term, make 1 plus and 1 minus. So here we have the rest of my roots. If all of these are equal to 0, then we would have to subtract the 2, so negative 2 is an option, a 0. We would have to subtract the 3, so negative 3 is another 0. And then we would have to add the 3, so that would be our fourth and final 0. Again, remember, we're supposed to have 4 zeros, and all of these numbers here are on my list. 1, negative 2, 3, and negative 3. Now let's look at a more challenging question. After the first half hour, the number of video games that were sold by a company on their release date can be modeled by g of x is equal to 2x cubed plus 4x squared minus 2x, where g of x is the number of games sold in hundreds and x is the number of hours after the release. How long did it take to sell 400 games? So how long? That means that we are solving for the time, right? The number of hours. And as you can see in the question, it tells us that x represents the number of hours. So we're looking for what x is equal to when we sell 400 games. And like in the question states, it says that g of x is the number of games sold in hundreds. So that means that we're going to make g of x equal to 4. We make it equal to 4 and not 400 because g of x represents the number of games already sold in hundreds. So if it's 400 games, that means that the actual value of g of x is 4. So let's set this up here. That means that this equation here, we're making it equal to 4. So 2x to the third plus 4x squared minus 2x is equal to 4. We can subtract the 4 to make it equal to 0. So 2x cubed plus 4x squared minus 2x minus 4 is equal to 0. Now remember, we do this because we subtract it over because we want to be able to solve the polynomial. And in order to solve the polynomial, it has to equal to 0. So this particular question can actually be used, you can actually solve this by grouping, but we're just going to practice using the rational root theorem. So right away, I noticed that all of these numbers here can be divided by 2. So we can just go ahead and do that. Let's factor out a 2, and we would get x cubed plus 2x squared minus x minus 2 is equal to 0. And then we can divide the 2 just to kind of get rid of it if we wanted to, since 0 divided by 2 is still 0. So my polynomial now looks like this. x cubed plus 2x squared minus x minus 2 is equal to 0. Keeping in mind that this is p and this is q. So if I do p divided by q, all of the possible roots here are plus or minus 1 and 2, since those are the only two numbers that multiply to give me 2. And then divided by the factors of q, which is just 1. So my possible roots here are only plus or minus 1 or 2. So let's test one out. Let's start with 1. If I start with 1, I'm going to put here my coefficients of the polynomial. So 1, 2, -1, and -2. Bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 3 times 1 is 3. -1 times plus 3 is 2. 2 times 1, 2. And I end up here with the remainder of 0. So I know right now that x is equal to 1. Now we need to factor this. Since I started with a cubic equation, this is quadratic, so this is x squared plus 3x plus 2. The two numbers that multiply to give me a positive 2 and add to give me a positive 3 would be 1 and 2. So we have the factors x plus 1 and x plus 2. Leaving me with the zeros, x is equal to -1 and -2. Now, remember that we're answering this question, we have to keep these numbers in mind, like when we're looking at the answer, we have to think about which one of these would be correct. X represents number of hours, so that means that -1 and -2 cannot be answers because hours cannot be negative. So that means that x is equal to 1. So that, again, to put in the context here, it took 1 hour to sell 400 video games. All right, now let's see how we can further narrow down our search for zeros. We're going to look at another theorem today, which is the Descartes rule of signs, named after the mathematician. Now, the Descartes rule of signs, what this helps us do is to narrow down the signs of the zeros or the roots. Okay, so now this may be a little bit difficult to kind of understand right off the beginning, but basically, if you compare the number of times that the sign changes from one term to the next, that's going to tell you how many possible positive roots you would have. And then whatever number you get, it's also, it could be that number or an even number or less than that number by some even number. So, okay, let me explain. And sometimes it's just easier to explain using an example. So what I do here is I compare how the signs change. From -3 to +2, it changed signs. Positive to negative, another sign change. And then negative to negative, 0 sign changes. So this means that I could have 2 positive roots, or an even number, or less than that by an even number. So what we do to figure out the other option is we would subtract 2 every time. So if I subtract 2, I would get 0. Now you would keep subtracting until you reach 0, because less than that you can't have a negative number of roots. So I can either have 2 positive roots or no positive roots. Now to figure out if we're going to have any negative roots, what we have to do is find f of -x. So that means that I'm going to plug in -x everywhere that I see an x. And now we kind of simplify this. -x raised to the third is going to remain negative, because a negative times a third negative is still negative. So if this is -x to the third times -3, that's going to make it a positive 3x to the third. This negative x squared, if this negative x is squared, then that negative x will become positive. So x squared times 2 would also remain positive. Then negative times a negative will give us a positive x minus 1. So now if I compare my sign changes, there's no sign change here, none here, but this goes positive to negative, so I have only one possible negative root. Now if I try subtracting 2, I would end up with negative 1. So remember, we cannot have a negative amount of zeros. So if you end up with 1, that means that that's the only option. You're only going to have one negative root. Now I have here a column for imaginary roots. And the reason for that is that here, remember that this exponent tells us that this is how many roots we're going to have. So if we have 2 positive and 1 negative root, that already gives me a total of 3, leaving no room for imaginary roots. But if I add here 0 and 1, this only gives me one possible root, and I need 3. So that leaves room for 2 imaginary roots. So basically, all of the rows here, if you add up the numbers, it has to add up to how many roots you're supposed to have. So now let's use the Descartes rule of signs and rational root theorem to help us find all of the roots of the polynomial. Okay, so let's start off by using the Descartes rule of signs, and I'm going to show you a little shortcut in terms of figuring out the negative roots. So from this term to this term, it went from positive to negative, so there is a sign change. Then it went from negative to positive, so another sign change. And then from positive to negative, so another sign change. So we have a possible number of 3 positive roots. And then remember, to get the other option, we just keep subtracting 2 until we get to 0. If I subtract 2, I end up with 1 positive root. And then if I subtract 2 again, I end up with negative 1. So I'm either going to have all 3 positive roots or only 1 positive root. Now a shortcut for negative roots is whenever you just flip it. So if you had a sign change here, when you plug in negative, you would end up with 0. So if you have a 0, you make it a 1. If you have a 1, you make it a 0. So if you have a 1 here, this means that there would be no sign change and no sign change. So, and we can test that, right? Let me show you how that would work. So if I plug in negative x, that means that I have negative x raised to the third minus 6 times negative x squared plus 11 times negative x minus 6. Negative x to the third would remain negative. This would stay positive because it's squared, so positive times negative 6 is negative 6x squared. 11 times negative x is negative 11x minus 6. And if you look here, notice how there are no sign changes. Every term is negative. So that's what I mean by this shortcut. You can take whatever you had gotten for positive and then just flip all of those sign changes. So there are no negative roots at all, which is nice because then that means that when we're testing numbers, we don't have to test any of the negatives. Now remember, we're supposed to have a total number of 3 zeros. If I have 3 positive roots, no negative roots, there's no room for imaginary roots. If I have 1 positive root and no negative, remember it has to add up to 3, so that must mean that I would have 2 imaginary roots. So let's start by testing out positive numbers. Well, first I need my list, right? So P over Q. P is 6, so the factors of 6 would be plus or minus 1, 2, 3, or 6. And then for the Q, it's 1, so everything is divided by 1. Remember, we have no negative roots, so we don't have to test any of these negative numbers. The only possible roots are 1, 2, 3, and 6. So let's start off by testing 1. Let's write out this polynomial. So 1, negative 6, 11, and negative 6. Bring down the 1. 1 times 1 is 1. This is negative 5. Negative 5 times 1 is negative 5. 11 minus 5 is 6. 6 times 1 is 6, and we end up with 0. So x is equal to 1 is one of my roots. So now I'm going to take this and I'm going to write it as the quadratic, which is x squared minus 5x plus 6. The two factors that multiply to give me positive 6 but add to give me negative 5 are x minus 2, x minus 3. And if I solve for each x, I get x is equal to 2 and 3. So these are my roots, 1, 2, and 3. So we ended up with this scenario. All of my roots here are positive, and look at my list, 1, 2, 3. So everything lines up. Let's try one more. All right, so let's use the Descartes rule of signs first. So we're going to check to see how many possible positive roots we're going to have. There's a sign change here, so 1. This goes from negative to positive, so another 1. Positive to negative, 1. Negative to positive, 1. So we have 4 possible positive roots. Subtract 2, I can also have 2 positive roots. And subtract 2 again, I could have no positive roots. If I just switch all of these, as you can see, we would have no negative roots at all. So now remembering that we have 4 possible roots, we either have, if we have 4 positive roots, we're not going to have any room for imaginary roots. If we have 2 positive roots and no negative, remember it has to add up to 4, so we could have 2 imaginary roots. And if we have no positive and no negative, that means that we would have to have 4 imaginary roots. So let's see which one of these scenarios it is. Now again, in this same scenario, we have no negative roots. So that means that we don't have to test any negative numbers. Let's do P over Q. Once more, we have 6 as my P. So the factors of 6 are 1, 2, 3, and 6. The factors of Q is just 1, so everything divided by 1 is still the same. So these are all of my possible roots. And remember that we are only going to test the positives. So let's start off by testing 1. I'm going to put my coefficients here. So 1, negative 5, 7, negative 5, and 6. Bring down the 1. 1 times 1 is 1. This is negative 4 times 1 is negative 4. This is 3 times 1 is 3. Negative 5 plus 3 is negative 2. This is negative 2. And we end up with a remainder of 4. So this does not work. Okay, so 1 is not a root. Let's try 2. Remember, we're only testing positive numbers. So again, 1, negative 5, 7, negative 5, and 6. Bring down the 1. 1 times 2 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 2 is negative 6. 7 minus 6 is 1. 1 times 2 is 2. Negative 5 plus 2 is negative 3. And negative 3 times 2 is negative 6, leaving me with the remainder of 0. So I'm going to start my list here. X is equal to 2. Now this is a cubic function. Let's see if we can solve that by grouping. So we have x cubed minus 3x squared plus x minus 3 is equal to 0. These two terms have an x squared in common, leaving me with x minus 3. X minus 3 have nothing in common, so I'm just going to put plus 1, and I'm left with x minus 3. So we can factor by grouping. We have x minus 3 as a factor, and what's left, the x squared plus 1 is my other factor. So I make each one equal to 0. So x minus 3 is equal to 0, and x squared plus 1 is equal to 0. Here we would add the 3, so x is equal to 3 is another root, which is also on my list. Then here I would subtract the 1, and I get x squared is equal to negative 1. And when I square root this number, I get x is equal to plus or minus. Keep in mind that this is a negative inside of a square root, so I. So my other remaining roots are plus or minus I. And this is a total of 4 roots because of the plus or minus. So we actually ended up here using this scenario. We have the 2 positive roots and then the 2 imaginary roots. And that's the rational root theorem and Descartes' rule of signs.